Exponential growth and decay. We're going to use two formulas primarily for these. P equals P sub 0 e to the kt. You may see it as y equals a e to the bx or a equals p e to the rt. It depends on your book and your instructor. I don't know what they're using. I'm going to use the p equals P sub 0 e to the kt. P is the final amount. P sub 0 is the initial amount. The 0 means nothing algebraically. It's just notation. E is the natural number. K is the exponential growth rate. We're going to express it as a decimal. And T is the time. Now if it's a growth, it's a positive exponent. If it's a decay, it's a negative exponent. And so let's do some examples. Now when you read this problem, it involves investing $100 at a 3.2% interest rate. We want to find the time it takes to double the amount in the account, and then we're also going to find the amount in the account after 10 years. So there's two different questions here. So I'm going to mark it as A and B. Now I can't use the compound interest formula because it doesn't say it's compound interest, so I won't know what N is. So I'm going to use the P equals P sub 0 e to the kt. It's like the compound and continuous problem. That's what we're going to assume. So we're going to assume all these are exponential growth and decay problems. So let's start. Now it says $100 is invested, so that's our P sub 0. 3.2% interest rate, so that's going to be our K as a decimal. It's 0.032. T, the time's what we're trying to find. For it to double, we don't know. Well, we do know how much it is if it doubles, because if you take $100 and double it, it becomes 200. So we're going to solve this for T, and it's going to answer the first question, question A. So first thing we want to do is divide both sides by 100. And we're going to get 2 equals, these will cancel out, e to the 0.032t. And then, since our t is an exponent, and it's in exponential form, I'm going to take the natural log of both sides. Now the good thing about this is, and if you notice, we have natural log of e. Well, we have a property that says if you take the natural log of e to some exponent, it always equals that exponent. The left side we just write down as it is. These like cancel out. Something I want you to realize, if you're asked to find how long it takes for something to double, that involves exponential growth or decay, what's going to happen is you're always going to divide by the number in front to isolate the exponential term. And that's always going to end up being a 2. And then you're always going to take the natural log of both sides, and it's always going to end up being the exponent. Remember, this exponent is kt. So we actually could have bypassed all this because it's going to be the same thing over and over again, and could have just used this doubling time formula. The natural log of 2 equals RT. Remember the R in the problem was 3.2%. As a decimal is 0.032. It's always going to end up being this. So it's just something you may want to keep in mind. You may forget it, but something worth remembering to save some time. So let's go ahead and finish this problem. So just divide both sides by 0.032. And since we are dealing with time, I'm going to go ahead and find the answer with the calculator. Approximate it. Natural log of 2 divided by 0.032. Remember, make sure you close the parentheses. And we get about 21.66 years. That's for it to double. Now we're going to answer the second question. We're going to use the same formula because this is a growth. It's growing, so it's going to be a growth. That's why we're using a positive. Now we're going to find the amount in the account after 10 years. Now keep this in mind. In 21.66 years, it's going to double to 200. So in 10 years, which is less than 21.66, it's not going to be it won't even be 200. It's going to be less than 200. So it's going to be between 100 and 200 when we do the final answer. So let's find out if we do the math correctly, and that turns out to be what it is. We know in 21 years or so it's going to be 200, but in 10 years it has to be less than 200, but more than 200 because that's what the initial value is, initial amount. K is 0.032, and then T in this problem is 10. So I'm just going to take out the calculator and we're going to try to type it in. Now here's how I type it in. I'll move it over here so you can see. 100. I'm going to use this E key over here. Exponent. Now I'm going to use parentheses. Now I'm going to type this in as 0.032 times 10. I don't want to get lost in all these parentheses, so that's why I'm typing in like this. Enter. And we get an answer that we would suspect. 137.71. And that is dollars. So be careful how you type it in, but not too bad otherwise. Let's do some more. We're looking at an asymptote that has a half-life of 2200 years. That means it's decaying. So if the initial quantity is 20 grams, find the rate at which it decays. And then we're going to find the exponential decay function, and then we're going to use that function to find the amount after 1,000 years. So what that's telling you is we have to find K first. There's 3 different questions here. So the first question is we need to find K, which is the exponential growth rate. And to do that, we're going to use this information. Half-life is 2200 years. The initial quantity is 20 grams. So this is a decay. So it means we're going to use P equals P sub 0 e to the kt. Or is it? Nope. It's a decay, so we'll use the negative. So we know that the initial amount is 20 grams. And we don't know what K is, but we know that it takes 2200 years for it to decay, so that's our T, to half its life. So half of 10, or half of 20, I just told you the answer. Half of 20 is 10. So after 2200 years, it decays from 20 grams to 10 grams. Now we're going to solve it using the same steps as we did in the previous step or problem. We're going to isolate the exponential part first by dividing both sides by 20, which is going to give us 1/2 or 0.5. And then I'm going to write this as negative 2200k. Makes it easier to see and to work with. And then, as we did before in the previous problem, when we get to this step and we're solving for the k, which is the exponent, or in the exponent, we're going to take the natural log of both sides. And what that means is we still have natural log of 1/2. And the natural log in e to an exponent means it equals the exponent. It's one of the log properties that you need to know. That's okay, because these like cancel out in a certain sense. So what I want to show you before we go any further is half-life. As before, you can actually bypass all the work that we just did and could have went straight to natural log of 1/2 equals, in this case, negative RT, because it's a decay. It always happens that way, because when you take a number, which is the initial amount, we won't end up with its half-life. You're always going to divide by that initial amount. It's always going to equal 1/2. And then we're going to take the natural log of both sides, and that right sides are always going to have the natural log and the e cancel out. It's always going to equal RT, or in this case, negative RT. So it's just a standard formula that you might want to use. Highly recommend it, but not required. It could be required, depends on the instructor. But let's go ahead and finish this. Solve this for K. Divide both sides by negative 2200. Let's take out our calculator. Type in natural log of 1 divided by 2, close parentheses, divided by negative 2200. Now, I'm going to show what that E means. What that E means, that means you're going to take this decimal and you can move it 4 places to the left. So that's approximately 0.1 1, 2, 3 places, and then 3, and then I'm gonna go to 1, 5. The more decimals you use, the more accurate it's going to be. So that's what that means. E to negative 4 is a scientific notation. Move it 4 places to the left. I may have said it right, but it's to the left. So that's our k. Now we're going to find the exponential decay function. So what that function is, it's this, and I probably should have been using this the whole time. P of t. Sometimes that extra variable gets in the way, so I've been leaving it out. But since it's asking for a function, I want to put in correct function notation. I'm going to use P of t because we know what everything else is. We know that P sub 0 is still 20. We know E is still E. We know it's a negative, but we found out what k was. 0.000315. So that's what we're going to use. 0.000315. And then t is the variable that we're using for our function. So a lot of these problems are done this way. You use the given information to find k first. Once you have k, that means you have a function in terms of t, which now means that you can use this to find the amount after 1,000 years, or really for any time. Once again, it takes 2,200 years for 10 grams or 20 grams to become 10 grams. So for 1,000 years, it hasn't reached 10 grams yet. It hasn't decayed to 10 grams. So our answer should be between 10 and 20. Let's substitute our values into the problem. So we have, in this case, our t is 1,000 years equals 20 e negative 0.00315. I'm going to use a times a dot symbol here. We're going to use 1,000. The reason why I'm using the dot symbol is so that we can type the whole exponent as one single exponent with parentheses. So let's type it in, see what happens. I'm going to move my calculator over. So we have 20 second e, and I'm going to type in, I'm typing in negative 0.000315 times 1,000. Close. And we're going to hit enter. We better get an answer between 10 and 20. And we do. That's what we were expecting, so that's what we get. We get 14 point, if I were to round off, 0.60. And that's in grams. So we're done with that one. And so, keeping that in mind, we're going to do one more that's going to follow the exact same process. This one's actually is a little bit more difficult because of a certain thing, because of the time is what it comes down to. But here's what we're going to do. The question is asking to find the exponential growth function, and then we're going to use that function to find the predicted population in 2010. Now here's the thing. We can't, our function, the formula we're going to use is p equals p sub 0 e to the kt. As of right now, we know that the initial amount, 2 million people, is our p sub 0. I'm going to use all the zeros just to be safe. And our final amount for this first information in the year 2000, there were 90 million. Now, we don't know what k is. It's not given anywhere. And in fact, we don't know what t is. Or do we? Well, let's think about it. In the first part of the problem, it states from 1930 to the year 2000. Well, how many years has elapsed? You should say that's 70 years. Well, that's our t for the first part. So this first part of the problem, we're going to find k. That's what this is doing. All the information was given to us. Sometimes you have to read it a little bit more closely. So now I'm going to divide both sides by 2 million. I know I'm leaving out commas. It's not that big a deal. Don't worry. And that means on the right side we end up with e to the 70k. I mean, these are all the same kind of steps we've already been seeing. I'm going to type in 90 million make sure you type in 90 million divided by 2 million. And yep, you better get that answer. And then what we're going to do, we're going to take the natural log of both sides. I'm just going to save some space by writing natural log in front of both sides. And we get natural log of 45. The natural log and the e cancel each other out, and it leaves 70k. Divide both sides by 70. I'm going to have to type that in my calculator because I need a decimal value. Natural log of 45, close parentheses, divided by 70. I'm going to round to 3 decimal places. 0.054. Maybe I go to 4. Let's be safe. 0.0544. So that's our k. Now, that means that our function is, well, I should be using p of t. Ooh, what was that? Ooh, that was crazy. P of t equals p sub 0, which is still 2 million, e, and we just found k, 0.0544, and we don't know what t is, so we're going to call it t, because we need a variable in our function. A function is our function. Now, we're going to use this exponential growth function to find the population of Brazil in 2010. That's the predicted population. Now, all we need is the t, but keep in mind, the 2 million was for the year 1930, and so for 2010, how many years has that been? 80 years. So that's how we find our t, or that we're going to use. So we're going to find p of 80. P of 80 equals 2 million. E. And by the way, and I haven't mentioned this yet, the population was increasing. That's why we're using the positive exponents. It's not a decay, it's a growth. So e to the 0.0544 times 80. And once again, I'm going to put that in parentheses just for the calculator. And we're going to type that in. I'm going to move that over once again. I cleared out so we can see it. 2 million. .0544 times 80. We get this number 155267149.8. 155,267,149.8. If you want to round up, it's 150. Probably should round up. I'm talking about people. I don't want to see 0.8 of a person. And so that's what we're doing. That's the same process as we did before, but it increased quite a bit. That's what exponential growth means. In 70 years, it went from 2 million to 90 million, and then, which is about, well, that is a growth of 88 million. And then in the next 10 years, from 2000 to 2010, it increased by what? 75 million more? Or 65 million more? That's a big jump. That's what exponential growth means. It's like the graph's going up quickly at a certain time frame. It gets bigger quicker. If you were to graph that, that's how it looks. Which I can't do that. More problem. Can't go negative values. Let's do one more. We're going to determine the number of years for an account to accumulate to $5,000 if $1,500 is deposited at a 3% interest rate, compound it monthly. This has the keywords I need to see for me to use this formula. A equals P parentheses 1 plus R over N to the NT power. And I have everything I need. Compound it monthly. That monthly means that's 12 times in a year. So this problem is a little different than other problems you may have seen in other videos that you may have watched of mine. This time the A is given. It's $5,000. That's the total amount. P is 1,500. That's the initial amount. Interest rate as a decimal is 0.031. Monthly is 12. But this time we need to know the number of years, which is T. So this is how this one's been different. This is the first time where we had to solve for an exponent in this compound interest problem, which means we're going to have to use, do I dare say, that's correct, logarithms. So let's divide both sides by 1,500. And what I'm actually going to do, I'm going to leave it as a fraction. I could use a decimal, but I don't know what your instructor wants, so I'm going to also leave this as a fraction, or as it is. Now you may want to use decimals, and that's fine, but it really depends on your instructor. So now I have this exponent, and I need to get the t, this 12t isolated. And in order for me to do that, I'm going to do something that you're probably not going to like too much. I'm going to take the natural log of both sides, which just means I'm going to write natural log in front of each side. So the left side, I'm not going to do anything with it. And once again, I'm actually probably doing it the hardest way. You probably want to use decimals, but to be safe, to get the most accurate answer, I'm going to do it as it is. What that means now, since I have natural log of something with an exponent, I can move that exponent out in front. And then, remember, the whole thing that I'm doing is trying to get t by itself. I'm actually doing the same steps as I did in the other problems. I'm just using a different formula. But there's a point where I'm trying to get the exponent by itself, so I have to take natural log of both sides. And what's different now is that I'm moving the exponent out in front. Now to get the t by itself, I'm going to divide by everything that's not a t, which is the 12, and then the natural log of all that. And so if your instructor wants the most accurate answer, this is what it would be. All this messy stuff. T equals all of that. Well, that is messy. But if they wanted an approximation, then you could easily have found the decimal for 5,000 divided by 1,500, and you could have found the decimal for 1 plus 0.031 over 12. It would have made the problem probably a little bit easier to look at. Now let's go ahead and see if we can find the decimal approximation for this, and make sure we can type it in correctly. So let's type in natural log 5,000 divided by 1,500. So that's one big number. We're going to divide that by, I'm going to use parentheses. I'm going to put all that in one big parentheses. 12 natural log of 1 plus 0.031 divided by 12. Closing it for the natural log. Close it again for the denominator. Enter. Ooh, what was that? Ooh. Don't need that. Delete that. Enter. And we get about 38.89 years. Make sure that's what the problem was asking. Yep, number of years. You should know by now when you're doing compound interest problems and you're trying to find out how much money you're going to make. $1,500 is a small amount. 3.1% interest rate is a low rate, and monthly is standard, and it's not very quick. So it's going to take a long time for 1,500 to become 5,000. So just be aware. In fact, you can see it takes 38.89 years. So you may want to rework that problem, but this part right here is the exact answer, and this is a decimal approximation. And you could have changed these to decimals very early in the problem if you want to save some writing. It all depends on what your instructor wants.